Welcome to Deep Engineering Live Interview Sessions. I'm Sakit Jha, Editor-in-Chief of Deep Engineering Publication and Weekly Newsletter. I'm glad you could join us for this session today, which is one of the most talked about and least understood technologies in our field. Our guest has worked across research as well as the commercial sides of quantum computing. Sebastian Hassinger is the author of The New Quantum Era. He led go-to-market for AWS Quantum Technologies and ran quantum business development at IBM. Let me bring Sebastian on stage. Sebastian, welcome.
Thank you, Sakib. Nice to be here. Thank you.
Great. Thank you so much for joining us today. Before we dive deeper and I start asking you questions, please tell us a bit about yourself, tell us a bit about the landscape, and yes, you have the floor.
Sure. Yeah, I mean, this has been, I have a long career in emerging tech going back to the beginning of the internet in the early 90s and, right through the World Wide Web, the emergence of that in the mid 90s. I built the first Apple support site on the web. I started a couple of internet service providers. I like to joke I started one too early and one too late. For my economic well-being. I've worked in innovation in large corporations, IBM, Apple, as I said, and others, and helped startups as an advisor, as a co-founder in some instances. And so I had this long career of going from one emerging technology area to another. And as I explained in the introduction of the book, I was helping IBM with their open source strategy for Qiskit, or I was asked to. And my first sort of action was to go to the Think Summit in 2017 at the TJ Watson Research Lab at IBM. And they were talking about the first 53 qubit machine that was going to be launched the following year. And it was completely mind blowing. It was about 95% incomprehensible to me, but I could tell it was very, very, novel and so early stage that I wouldn't have to look for another emerging technology area for the rest of my career. And I've always been extremely interested in quantum physics, quantum mechanics, although I don't have a physics background. So it started a kind of obsession. And I within a year, I was working on the IBM quantum team. And I've, sort of now over almost a decade now, I've been trying to learn more about the science that underpins this incredible technology, and also just understand how it will fit into the broader landscape of classical technology, which I've made my entire career from. So that's kind of the context of the book and the podcast as well. I interview researchers weekly, and it's the same name as the book. And the basic sort of framing of those interviews is, please explain to me as a non-physicist what it is you're doing, because it's really interesting. So that's kind of, that's it's become, as I said, a kind of obsession, but it's a very enriching one because it's a very interesting field.
I'm sure it's exhilarating and mind stretching.
It is.
So
Yeah, and you asked about the landscape. This has been in one way, it's been a very long road, but in another, it's actually sort of startlingly fast, because the idea for quantum computing theoretically has its roots in the early 80s, but it wasn't really until around 2000 that there was physical qubits being made, and sort of experimental proof that you could actually make qubits and do computations with qubits. These are the equivalent of transistors of bits in classical computing, are quantum bits, or qubits for short. And so that's really 25 years. We're now at right near the verge of building quantum computers that actually can do things that classical computers truly can't. We everything we've built so far has been experimental and research and development, with the aim of research and development. And really, you can, your laptop can simulate a quantum computer better than a current quantum computer can. So, but that's changing very rapidly. And as I said, we're right on the cusp of but certainly before the end of the decade, where we'll see machines that are at a scale that they can do meaningful work that you can't do on a classical computer. So that's the sort of I think the reason that's driving a lot of the increase in interest recently.
yeah, that is exciting. Thank you. So a quick note to our audience, please feel free to interact. There is a chat box. There is also question and answers. You can just post questions over there. I'll be showing them on stage while I'm also asking questions to Sebastian. So what we will do now is I'll just ask you some of the basic questions.
Yeah.
Before we
Please.
actually get specific about what quantum ready means for the people in this room. We'll also be featuring this conversation in one of our newsletter issues. So please subscribe to Deep Engineering newsletter. I'll be posting the link in the chat very soon. So yeah, let's get started. Awesome. So Sebastian, please strip away some of the metaphors for us and tell us what is a quantum computer actually doing that
Right.
the machine.
Yeah. So there's a couple of ways to come at this, and there are a lot of, as you said, metaphors that are used that are misleading at best. So I'll try a couple of different sort of ways that I have found make sense to me. On the one hand, the difference between a classical computer and a quantum computer is that a classical computer is made by etching and creating depositions on silicon, and essentially you're creating physical circuits that turn on and off to represent logical operations. Right, the Boolean logic is the at the root of everything a classical computer does. In the qubit, in the quantum bit, you're using what's called a two-level system. So a system from nature, it can be in an atom, it can be in a superconducting circuit that's acting as if it is a quantum particle. It can be in a photon, but something from nature that has two different energy levels that you can control. So you can put it in the ground state or in the excited state, and you can differentiate between those two states. And those two states become the 0 and the 1. We sort of project those values onto it that you then use in your algorithm, your computation. As a result, it sounds like it's still binary because it's 0 and 1. However, those energy states can exist in a superposition, which is a quantum mechanical behavior where the value is essentially a wave function, and it's somewhere probabilistically between the values of 0 and 1. It's in some ways both of those values, or it's some combination of both of those values. And so a single qubit is essentially a vector. And because you have a collection of vectors in a quantum computer with qubits, you can actually do linear algebra with those qubits instead of Boolean logic. So one of the ways to think about quantum computing is that the native language of the machine is linear algebra, whereas the native language of a classical computer is Boolean algebra. And linear algebra is very, very good at handling very high dimensionality kind of problems where there's a lot of interconnectivity between the variables, where one of the examples that's often used to illustrate this is although the physicists will quibble over the accuracy again, but it's easy to understand, is the traveling salesman problem, right? And this is trying to find the optimal route for a salesperson to visit all of the cities that are within their sales territory. That's a combinatorial problem. You just have to try all the combinations. There isn't really a shortcut. And when you add another city, cities becomes n+1, you've doubled the number of combinations that you have to test. And that's the nature of Boolean algebra. Every time you add another element to a fully connected set, you've doubled the number of combinations. In linear algebra, in qubits, you only need to add one more qubit, essentially. I'm oversimplifying, but that's essentially the deal, right? So whereas the number of bits you would need would double, you'd only need to add a single qubit to expand the computational space sufficiently. And so when you see things about quantum computing that say, for example, it would take more bits than there are atoms in the universe to compute, the computational space of something like 256 or 300 logical qubits. That's what they're talking about, is that the qubits become the exponent for the computational space instead of just the numerator. So that's I think the mathematical explanation. The other sort of intuitive way to come at this is that you're using systems from nature, quantum systems, many body systems, to carry out computations that help you simulate many body systems from nature. So quantum mechanics Feynman said at the Endicott conference in 1981, which sort of was the starting gun for the field of quantum computing, that it's computing systems from nature is inherently difficult because of that sort of exponential complexity that is inherent in these many body systems. And if you had a quantum computer to simulate those quantum systems, it just stands to reason that that would be more tractable as a problem space. So that's the other sort of very simple way to think of it: is if you want to simulate systems from nature, you need a system from nature. Is the pithy way to say it.
Interesting. That was exceedingly clear, and I'm sure very helpful to our audience, although slightly difficult for me to understand everything about it. But thank you so much for being very clear.
Feel bad because quantum mechanics is famously difficult, non-intuitive, difficult to understand, and even the field itself has sort of unresolved questions that any quantum physicist will tell you, well, we don't really understand quantum physics, so you're excused if you don't understand. I certainly don't.
Yeah. But on that note, superposition and entanglement also get thrown away, loosely.
Right.
So please, if you could expand on which one do people most often misunderstand, and tell us maybe what is the correct intuition.
Yeah, I mean I think the biggest misunderstanding, it's more of an ambiguity, I would say, is that it's often said quantum computers can test all solutions simultaneously and then select the right solution. That's not correct, literally. However, it's usually what the that confusion arises from probably the most famous quantum computing algorithm, which is Shor's algorithm, which Peter Shor discovered in the early 90s. And it's the one that will allow us to decrypt RSA and other asymmetric keys, key-based encryption methods. And it achieves that shortcut to factoring the key, the encryption key, or a very large number, down to its primes, which is the basis for all modern encryption, or most modern encryption, by doing what's called quantum phase estimation. And within that very large computational space that's created by a bunch of qubits that are entangled with one another, that very, it's referred to as a Hilbert space. So it's essentially 2 to the power of the number of qubits you have as your computational space, the theoretical limits to your computational space. What it does is it creates an interference, purposely creates an interference pattern, so that the wave functions of the equation are creating interference with one another, and the correct answer gets amplified, the incorrect answers get suppressed. So that is similar to trying all problems at once. I actually interviewed Peter a couple of times, and the last time I talked to him, I asked him how he felt about that. That when he hears somebody making that mistake of saying it tries all the solutions at once and selects the right one, and he sort of thought about it and he said, "Well, I mean, it's not really wrong." So it's with all things quantum, there is no real black and white, because I mean, I think the thing that is, again, very intriguing to me about this from the very beginning is that it's all of this behavior, all these attributes exist so far from our lived experience. It's not the physical world. We can't project even physical and human metaphor into the quantum scale, the quantum realm, the quantum universe, without making these kinds of very inaccurate kind of generalizations or misconceptions. So it's kind of one of the things that's fascinating to me, is the communication challenge of trying to grapple with these extremely ambiguous and foreign kind of ideas.
Interesting. Thank you so much for explaining that. We do have a question from somebody in the audience, and I will just show it on the stage. Maybe if you are already going to address that later, maybe we can take it up that time, but I would like to show it because it helps to move faster.
Sure. Okay. So this is referring to the potential that's often spoken about for quantum computing, quantum computers, to help in in the development of AI. I assume that's what's meant by model training is machine learning models or LLM models. This is interesting. However, I always caution people that there's sort of intriguing early results from quantum machine learning, but there's nothing conclusive about what quantum computers will or will not be able to do for machine learning or AI. I think it's far more compelling, and this may be why the quantum machine learning sort of thread continues to perpetuate or gets misconstrued as being something coming in the immediate future, is that AI or machine learning for quantum is an extremely powerful sort of category and has a lot of promise for things like error correction, for example, or helping with design automation or even algorithmic exploration and research. So that's happening today. In fact, I'm a fellow with the Unitary Foundation, which is an open source foundation for quantum computing software, open source software. And the team is about to release an LLM auto research framework. So it's a whole set of agent.md and instructions and a coding framework for LLMs to help you do very, very efficient research into error correction codes. So it's a search for efficient error correction codes that's leveraging LLMs in a really powerful way. So, I think there's immediate benefits to quantum from current AI models and machine learning more generally. Whether quantum will be useful for AI will remain to be seen. But I know there's a few different ways in which they're hoping that, the researchers who are working in quantum machine learning are exploring. One is, it was some work around state vector machines, which ultimately didn't show any actual advantage, but it's still an intriguing sort of area where maybe more capable quantum computers will be able to make a difference, which was coming back with the classification more quickly. So there was a hybrid loop between the classical computing, which would sort of estimate a curve and then send the estimate to the quantum computer. It would be able to classify the result more efficiently. This was the hope. It would classify it more efficiently than the classical would. As I said, the early experiments, as far as I know, have not proven to be the case, but there's still some hope that there would be some ability to get that kind of acceleration or more efficient classification when training models. And the other that I've heard about is synthetic data. So providing data sets to train models is starting to become a bottleneck because the LLMs in particular have already ingested all the data of the internet. And it's getting harder and harder to find data to train models that's not already the product of a model, which obviously you want to avoid sort of the snake eating its own tail of AI models being trained on the output of other AI models. So there's some interest in seeing if quantum computing can create synthetic data that doesn't suffer from the same sort of echo chamber effect that a classical AI model produced data would. So because the classical model is trained according to the constraints of the model, the data it produces is already sort of pre-weighted according to the model that generated, if that makes sense. And there's some thought that the quantum computer, because it does operate in this probabilistic way and also in a truly random way, you can actually get real random numbers out of a quantum computer. So there may be some value in synthetic data that can be generated by quantum computers in the future.
Awesome. Well, thank you so much for answering that. In fact, we have another question that I think I can show on stage. It is by Elizabeth. I'm not sure how to pronounce that. I'm sorry, but here it is.
Oh yeah. Okay. So it's an interesting question. There's actually a quantum algorithm zoo. It's a site that a university in the United States maintains. That's sort of a catalog of all the algorithms we know today. It's a surprisingly small number, actually. I mentioned Shor's. That's definitely the most famous. There's a Grover's search algorithm that's a certain type of search that is more efficient than a classical search in a particular set of circumstances. Excuse me. there is HHL. So there's a few algorithms that have a theoretical proven advantage. It's a small handful, and then variations of those algorithms. There's a lot of sort of fanning out variations of those algorithms used in slightly different ways. But it shouldn't. I used to think that was surprising and sort of worrisome that there wasn't a larger set of algorithms that we knew would be more efficient on a quantum computer. However, if I think back, because really, as I said, my professional career has all been in emerging tech, but emerging tech, the way we have experienced it, has all been incremental change on the base of classical computing. If you look back at the roots of classical computing in the middle of the 20th century, sort of post World War II, is when it really started to get going. They didn't know what those machines were going to be good for, and they didn't know for a long time. And I have one example that when I struck on, I realized we should not really worry about the lack of algorithms, because in Princeton, von Neumann was leading a team to build a system at the Institute for Advanced Studies. It was contemporary with the ENIAC device that was being built at Penn around the same time. So this is the late 1940s. Both were motivated by the difficulty of the physics calculations that the Manhattan Project and other wartime projects required. So these are physics calculations that were just getting more and more difficult for humans to carry out with pen and paper and slide rules and the like. And so a lot of what they were doing was trying to accelerate physics calculations, mathematical calculations for physics experiments. And there was a mathematician named Stan Ulam who worked with von Neumann, who came up with a method for calculating neutron diffusion based on sampling algorithm. He called his algorithm the Monte Carlo algorithm, which should be familiar to anybody who works in computer technology. And it wasn't until over 30 years later that someone got the idea to look at whether Monte Carlo might be useful for optimizing a portfolio. And so the technique that Ulam created, wasn't seen as a useful algorithm for decades, until decades later. And I think hopefully it won't take us 30 years, but I think the same pattern is going to very quickly assert itself when we start building these machines that are capable of doing all kinds of stuff that classical computers can't. What I mean is that they'll be able to simulate many body systems that classical computers can't. They'll be able to do physics experiments that classical computers can't. And the physicists and the chemists will be using them for solving their problems, which will be very narrowly cast, but the techniques they'll come up with will very likely yield sort of secondary or unexpected value in other contexts. So the trick will be for us to watch very closely what these early users of these powerful quantum computers are up to, and trying to be creative about understanding the technique they're using and seeing if there are ways that we can generalize that technique into an algorithm that has value in other industries, other use cases, commercial value, et cetera.
Great. Thank you so much, Sebastian, for explaining that question in detail. Mark it as answered. Thank you guys for asking these questions. They are very technical, very good. So keep them coming while I continue asking the basic questions to Sebastian. All right. So let's also talk about where quantum wins and probably where it does not. So where does quantum generally have an advantage, and where will classical computing stay ahead for the foreseeable future? If you could please shed some light.
Yeah, absolutely. It's a really interesting question. And it's another one of those areas that's often misunderstood. People, who are coming to the field or the topic at first might think, oh, it's, they're faster, or there is bigger data or whatever. It's actually, they're slower computers and they're smaller data. We're talking about qubit counts now in the hundreds. We're hoping to get to thousands. We might get to 10,000s. It's really important to remember that qubit count is effectively the register size of that computer. I mean, QEra's device, Aquila, which is 256 qubits, it's a neutral atom device. that you can load 256 bits of information into that device at a time. That's how large its register space is. So that does not sound very impressive. And so certainly classical computing will maintain an advantage for the foreseeable future in terms of the volume of data it can process and the speed with which it can pipeline that data, right? So when you're talking about just Boolean systems, logical, ones and zeros, classical bits, we now talk in terabytes and terabits per second, and that's a long, long way away, if it's even possible in quantum computing. But that's really beside the point, because as I said, you think about those 256 qubits. That's if you entangle all those qubits with one another, you've created a many body system that has 2 to the 256 states, right? I mean, the state vector is 2 to the 256. That is more atoms than exist in the universe. So you can't physically recreate that Hilbert space, that computational space. It's so when the data set, when the problem has to do with high dimensionality, very interconnected data, the quantum computer has a natural advantage because of the nature of, as I explained before, the Boolean logic versus linear algebra. Essentially, those are when you're dealing with vectors, you can actually model very high dimensional space that is very, very difficult to represent in a Boolean system. So that's kind of the rule of thumb. And the other goes along with that is that those types of problems are abundant in nature, in systems from nature. And by that, I mean, not just physics, although, material science, for example, that's condensed matter physics. It's how atoms pack together into a lattice, into a crystalline structure, how materials behave as a result of the packing. That's all physics simulations, or physics calculations. So quantum computers are very, very likely to be extremely useful in material science, which I think is very exciting. It's one of the things that I think is underestimated in terms of the potential impact. Because if we think about, there's some very interesting research that's been going on and progress being made around battery technology that's using quantum information, quantum technologies, or quantum computing to help with the design and the invention of new battery technologies. There's a hope, there's sort of an aspiration that if we can simulate materials very precisely in a quantum computer at a sufficient scale, we can actually sort of create designer materials, right? So maybe much lighter for the same strength, or maybe much stronger for the same weight, or maybe photosynthesis built into the actual material itself. So you'll coat your car with something that actually generates electricity without any kind of cells on the outside. I mean, the imagination sort of is stimulated by the idea of being able to engineer at an atomic scale the attributes of new materials. But that also extends into other physical sciences. So chemistry is at its core quantum mechanical, because it's the way that atoms interact with one another, and that is a quantum mechanical phenomena at scale, which means it's also very, very difficult to simulate precisely. So they talk about small molecule chemistry being sort of the next frontier beyond material science, likely to be able to make a difference. And then there's a very natural leap from small molecule chemistry to pharmaceuticals generally, which tend to be larger and more complex molecules. So you'll need a bigger and bigger quantum computer to be able to simulate them. But provided we can build a quantum computer large enough to simulate the types of molecules we look at for drugs, and the way those would interact with the systems they're meant to target within the human body, you can very easily imagine sort of a future where drug discovery and research is happening in this very, very high fidelity simulation in a computer, with all of the attendant sort of acceleration and benefits of that we're used to from computer simulations, right? It means the drug discovery pipeline could be compressed quite a bit, because you might be able to, screen a whole bunch of drug candidates with very high fidelity simulations of how their behaviors would present themselves in the real world before you ever formulate the drug itself. And then by the time you're formulating the drug in the real world, you already know how it's going to interact with the human system. So we might see massive acceleration in drug discovery as a result of quantum computing. So those are the easy answers. It's systems from nature in physics and chemistry in particular. Beyond that, people talk about optimization. They talk about sort of the Shor's class of cybersecurity or other sort of mathematical, broadly applicable mathematical algorithms. Those are all. I mean, as I said, we know a small number of them. The rest are going to sort of fall out from our use of these devices that can't be simulated classically. It's sort of a chicken and egg problem. We don't know what they'll be good for until we make them. We know, as I said, we know all the physical sciences. We'll definitely excel in those, but then the broader horizontal or finance industry or logistics or all of those other industries may find applications that we just don't expect right now because we can't imagine them because the computer doesn't exist at that scale yet.
Interesting. Thank you so much for that brisk answer. I do have a follow-up question on that. A lot of enterprises also assume quantum will kind of speed up their existing workloads. So tell us maybe for which problems is that assumption just wrong?
Yeah, I mean, as I said, the easiest answer to that is if you're talking about large volumes of data that need to be processed quickly, that is not going to be sped up by a quantum computer in the near term, and maybe never, because classical computing keeps advancing as well as quantum computing develops. So it may be a game that the classical always maintains the lead on. The It's difficult to, I mean, I don't want to say never around any of these things because it's very possible. As I said, we're in this kind of chicken and egg situation where, look at in chemistry, I mentioned, the potential for sort of higher fidelity simulation. What do I mean by that? Well, in classical computing, we are creating approximate simulations, right? So for chemistry, there's algorithms like DMRG and others that throw away a lot of the information about the chemical reaction because it's just too much to calculate. So we've devised these methods where we try to algorithmically sort of focus on a very small set of the problem that we hope is the most significant to the solution. And the promise of quantum computing is being able to not throw away as much data, have a much higher fidelity simulation that actually captures more of the dynamics in that system more accurately. And so I think that's sort of what I think about in terms of looking at enterprise use cases. Are there use cases and contexts where the data is very high dimensional? And I mentioned optimization. That definitely is an area where there's potential for a larger scale quantum computer to be able to do more efficient sort of optimization problems than max cut and the other sort of classical approaches, strictly because in optimization problems there is the same sort of challenge, which is the more interconnected the parameters of that you're trying to optimize around, the higher dimensional the problem and the more difficult the combinatorial problem is. So similarly, you can imagine a quantum computing approach that uh, that that can outperform a classical optimization by representing that dimensionality more efficiently and calculating more efficiently. But I mean, it does take. This is why it's, I think, smart for enterprises to start investing in the skills that you need for understanding quantum information and exploring potential algorithms now, even though the computers don't exist that can actually run anything useful now, because it takes a lot of effort to sort of recast. We've been thinking about these business problems in classical terms, in Boolean logic terms, since the middle of last century. So closing on 100 years now. I mean, well, it'll be 100 years and not too long. It's 70 or 80 years now, 80 years probably. And that's a very deeply ingrained set of preconceptions around problem solving, right? So we're looking at our world through the lens of how could my laptop fix this problem, right? We write code on machines, and our minds are thinking along the lines of like decomposing the problem and figuring out what the dynamics are and how to represent them efficiently, all rooted in this invisible reliance and assumption that at the ground level you're doing Boolean algebra to solve the problem. So I don't think we're fully aware, or not many people are fully aware, how much our thinking, our problem solving thinking is rooted in the way classical computing works. And it's so different in quantum computing that building up, people talk about quantum intuition, right? It's developing that mindset of looking at the world through the lens of linear algebra and the dynamics and capabilities of quantum information takes a lot of work. So, some of the smartest enterprise approaches to quantum computing that I've seen have been hiring a small number. JP Morgan, for example, Russ Lund leads the team there, and he's doing research with quantum computing hardware companies and academic researchers that are at the top of the field. And they're looking at problems that are within the universe that you can imagine. JP Morgan has a very large set of challenges and algorithms and tasks that they need to carry out to operate such a large financial entity. And so they're looking at theoretical problems that have some kind of mapping to an aspect of their business processes, and then doing this sort of exploratory research. Then they publish open science papers, so everybody benefits from the work that they're putting in. But they're building up the muscle for JP Morgan to be able to apply quantum technologies when they mature to a sufficient scale. They'll know how to use them because they will have been building that muscle ahead of time. And I just think that's a very, very smart approach. It's difficult for a CTO or a CIO to make that choice because it's not a clear ROI, right? It's not, I've got here are my top 10 problems. Here's how much budget I have for R&D or advanced technology or other sort of more applied areas of investment. I'm going to deploy this capital and these resources according to the highest payoff, calculated payoff. You can't put a number on quantum computing. And that makes it difficult to make that investment and sustain that investment. But increasingly, people are seeing that that's something that they have to just sort of work around and make an exception to the way they normally prioritize investment. And I think that's a healthy thing across all industries.
Great. Thank you so much for patiently answering my questions. And
of course, my pleasure.
I do have a couple more questions. But I know that people might also ask questions, so we have to be, guard the time. So maybe briefly, if we could just discuss something about the hardware, if you could provide maybe a brief download on the hardware side of things. How far are we from the machines that actually do useful work beyond what classical systems already handle?
Yeah. I mean, in some ways, we've already past that threshold. The Quantinuum device, I think they had 12 logical qubits. They've done some random circuit sampling with error correction on their device that would be difficult, if not impossible, or very, very long to simulate on a classical computer. It's an artificial problem, right? The problem is designed to be difficult for a classical computer, which has been, that has been the sort of standard operating procedure all the way back to Google's announcement that they had achieved quantum supremacy back in 2019. That was also random circuit sampling. So what they're doing is creating random quantum circuits and then sampling those from the quantum computer, which obviously that's a natively quantum operation. So it's more difficult for a classical computer to simulate. So, you're sort of purposefully creating the problem to make it difficult for classical. But you asked about useful problems. That's a little bit harder to predict. However, all the hardware companies, all the sort of leading hardware companies across modalities have roadmaps that deliver machines before the end of this decade, sort of in the 2028, 2029, 2030 kind of range, which have the promise of clear advantage, right? So there's sort of a general rule of thumb that I've heard a number of times from physicists where it's sort of like 50 logical qubits. And these are logical qubits means they're fault tolerant. So they're error resistant. If an error occurs, it can be fixed in a reasonable amount of time. So 50 logical qubits or fault tolerant qubits that are fully connected with one another creates that you're talking about a computational space of 2 to the 50, as we mentioned before, and that's beyond the scale of the largest supercomputer we can imagine building. 2 to the 50 bits is enormous computational space, and therein lies the challenge, right? So if you get to, let's say, roughly that scale, 50 logical qubits that are all fully connected, you're at that point, anything you do on that machine is impossible to do on a classical computer. So if you can find useful things to do on it, they will by definition be quantum advantage that you can't do classically. At that scale, in the 50 to 100 logical qubit scale, as I said before, the candidates for useful work are all going to come from physical science, because it's very, very, if you look into quantum stimulation, so there's classical quantum stimulators, right? There's software packages, both open source and otherwise, that are out on the internet that you can run on classical computers and stimulate the operations of a quantum computer, simulate the quantum circuit being solved. If you look closely at the number of qubits that's being simulated, some of them say 300 or hundreds of them. They're doing that with tensor networks, and they're doing that in very sparse connectivity. So very few of the qubits are connected or interconnected with or entangled with one another in those scenarios. Because when qubits are not entangled, it's much, much, much more easy to simulate those devices. So again, it's the number of error-corrected qubits and the connectivity among those qubits is really the set of characteristics you need to look at for the comparison of performance from classical to quantum. And as I said, IBM is talking about delivering a device that's clearly beyond that classically simulatable regime by, I think, 2029 is when they're predicting. QEra's got a device that's coming. Quantinuum's got a device that's coming. IonQ's got it. So there's probably 5 to 10 credible hardware roadmaps. Credible meaning there's enough detail that you can actually see how they're planning to achieve those devices that will deliver that kind of performance. What's fascinating to me is that across all those vendors, there's a number of different, we didn't discuss this, modalities or ways to make qubits. As I said at the beginning, a qubit is just a two-level system. It's something that can be put into a ground state and an excited state in a controlled way, and you can read out that state, and therefore that can be a qubit. So we've got a number of different approaches. At IBM, I mentioned, where I worked first, has superconducting qubits. They make circuits made of superconducting material with a junction that breaks the circuit that actually it's called a Josephson junction that when it's a superconductor, it's actually exhibiting behaviors in that junction or in the whole device that are quantum in nature or in their behavior. IonQ, Quantinuum, they both trap atoms or ionized atoms in a laser trap in a vacuum, and then manipulate them with lasers. There's other atom-based devices called neutral atoms from QEra, Atom Computing, Pascal, and others. Even within one modality, neutral atoms or trapped ions or superconducting, one vendor's qubits are not the same as another vendor's qubits. So there's an enormous amount of diversity. And in a way, if you think back to the analogy of the classical computing industry and or the technology, how it developed, we're in this stage that's sort of pre-transistor. When Bell Labs invented the transistor, vacuum tubes very quickly disappeared, and other ways of doing computation very quickly disappeared. Gears and other sort of exotic early stage computing technologies all disappeared because the transistor was so clearly superior. And then for scaling, Texas Instruments and Fairchild both hit on the idea of printing circuits, of integrated circuits that could be printed on semiconductors, and that immediately destroyed all of the industry built around the individual components you would solder together into a big device, because it was so clearly superior. So there's these two moments in classical computing, the transistor and then what's called the monolithic solution, which is the integrated circuit, that were like evolutionary events, where there was all this diversity and fragmentation and innovation going on in all these different ways. And then there's this moment, and it's like, okay, everything from now on is transistors. And then there's this other moment, it's like everything from now on is just a printed circuit. We haven't had those moments yet in quantum computing. We're still in that very diverse, fragmented, lots of innovation, lots of creativity. There's now close to 100 quantum computing hardware companies, which is clearly not sustainable, but it's an indication of how much effort is being put into trying to come up with that solution that in retrospect is so obviously the right solution that it sort of, squashes a lot of its competitors. I say a lot because I think that some people say like which type of qubit is going to win. I think it's actually not a singular answer. I think there will be multiple modalities that have a significant amount of life to them, of future development to them, because they have different strengths and weaknesses. And it's unlikely there isn't a candidate in the near term that seems to sort of tick all the boxes and make all the other solutions irrelevant. But I do think there will be, the race right now is towards that threshold of like a machine that can operate at scale with fault tolerance sufficient to deliver a device that, again, is just not physically simulatable for a classical computer. Once we get to there, we're going to see, I think, a narrowing of the field, but it won't collapse just to one type of qubit for one vendor for a long time.
Great. Thank you so much for that answer. I actually do have a question around evaluating the vendor claims, but I do want to ask about error correction first, and then I'll circle back around evaluating the claims. So if you could also shed some light briefly on, error correction keeps getting described as a bottleneck. So what actually changed in the past year, and tell us what has not maybe.
Yeah. Quantum error correction it's very challenging. I mean, we dealt with error correction in classical computing primarily through redundancy, right? If you encode a value in 5 bits and then you read that value out and 4 of the bits or 3 of the bits agree and 1 or 2 are different, then you go with the majority and you just say, okay, that's what the value of that is. That's, it's very simplified, but that was the original sort of approach to error correction in classical computing. It's gotten more sophisticated and less necessary because we've got more and more precise devices. Qubits are incredibly error prone. It's very, very, very difficult to get high fidelity gate readout and performance from a qubit because you're talking about, for example, a spin of a single atom that you're hitting with a laser. You can imagine somebody runs the microwave in the other room or whatever, and that could interfere. It's very, very delicate. They're very shielded, but it's still really difficult to get that kind of performance. So error correction is incredibly important. But there's a thing called the no cloning rule, which exists in quantum mechanics, quantum information, which says that you cannot have a copy of a qubit's value. A quantum state that encoded in a qubit, once you measure it, disappears. So it's really, you can't just do pure redundancy and just have, the same quantum state encoded in multiple qubits and then just majority rules. If 2 of the 3 are the same, that's what you go with. So Peter Shor, in fact, invented quantum error correction, or in large part was responsible for quantum error correction, which is a great story because he came up with the factoring algorithm that factored a large number to its primes. And the community said, his peers said, that's great, Peter, but if we make quantum computers, they're going to be so noisy, you're never going to get, fault tolerance. You're never going to get error correction. So within a year, he wrote the first paper on quantum error correction. So he was like, a challenge accepted. I think it's a great moment. But essentially, in simple terms, what quantum error correction is it's a whole bunch of different approaches to the same basic thing, which is making the qubits arranged and interdependent in such a way that if an error occurs in your data qubit, one or more ancillary qubits will change their state in in a way that you can detect. So in other words, you can't look directly at your data qubit, but you can look at these ancillary qubits. And if one of them changes, you know something happened to the data qubit, and you can then apply some kind of correction. So it's very complicated math. It's the one of the sort of leading codes that what Google actually implemented on the Willow chip. So this is a year and a half ago now, was what's called surface code, which is a topological, a mathematical arrangement of value in a lattice of qubits that does this kind of sensing of errors. That was this very significant research result because it was the first time that someone had demonstrated that you can actually experimentally achieve surface code error correction on a physical qubit and deliver performance that actually improves. The more qubits you put in the surface code, the better the result they were getting, and the more resilient the information system that they were encoding in that surface code was. So that was sort of, I think, in a way, the whole industry is kind of holding its breath about error correction and going like, "Ooh, I really hope it works," because if it hadn't, we would have been stuck in this kind of noisy qubit regime that is interesting from a scientific perspective, but was unlikely to show any kind of commercial value. So that was November, December of 24. Since that time, over the last year and a half, there's been all kinds of both theoretical and practical breakthroughs that are kind of accelerating the the timeline of error correction and fault tolerance at scale. One of the things that happened was another sort of family of error correction codes from classical computing called low density parity checking, the LDPC, was adapted to quantum. So this is an easier method to implement than surface code. Surface code is challenging in some ways. It's very good, but it's also very challenging to do at scale. So IBM, for example, has published a paper describing the way they're going to use QLDPC or quantum LDPC error correction in their next generation devices, where 288 qubits, physical qubits, are going to yield 12 logical qubits with a significant resiliency of the error correction. And that's kind of what their roadmap is looking like now, is this LDPC based, they call it bivariate code that's delivering logical qubits. And there's variations thereof. And then on the theoretical side, so all the hardware vendors are working out how they're going to deliver error correction and resiliency. On the theory side, there are really like leaps and bounds of gains in efficiency in the way that Shores in particular is being delivered. So the number of physical qubits you'll need to run Shores at scale has gone down several orders of magnitude. When the first estimation happened back in the 90s, when Peter originated the algorithm, I think it was 20 million physical qubits is what the estimate was. Most recent, so Craig Gidney at Google about a year, maybe two ago, had a new resource estimate. I think it was 2 or 3 million physical qubits. So that's an order of magnitude. And then Pinnacle in Australia came up with this algorithm they call Iceberg, or an approach called Iceberg, which I think reduced it to 100,000 or 300,000, something like that. So hundreds of thousands. So that's another order of magnitude down. And then a new company launched out of Caltech just this spring. They wrote a research paper. It's called Oratomic, ORO, I think, Oro A Atomic, I think. But anyway, Oratomic. And they wrote a paper in the spring that claimed something like tens of thousands of physical qubits, something like on the order of 10 or 20 or 30,000. So tens of thousands to run Shores in a way that would crack an actual real world encryption key and raise $300 million on the basis of that research paper. So you can tell that the anticipation, like these two sort of vectors are converging. Like we're getting real implementations of error correction with practical roadmaps saying we're going to deliver this many logical qubits on this kind of timeline. And then on the theory side, you're getting increasing efficiency out of the way the resource estimations are trending, the way you're implementing it in a theoretical quantum computer. And those two lines are converging much more rapidly than I think people thought maybe a couple of years ago. So that's kind of one of the major drivers, because obviously if we get a machine, in a small number of years, in single digit years, that can crack, popularly used classical encryption methods, that'll be a significant event, and one that, the governments of the world, for example, are very interested in predicting, forecasting, and mitigating the risk of. So that's driving a lot of the conversation these days.
Great, great. Thank you so much for answering that. Yeah, and I also want to circle back to the question I had earlier about evaluating the claims. You did mention that briefly, but maybe if you can also just explain that.
Mm.
So when a vendor announces a new qubit count or a new milestone, so what should a technical leader look for before taking it actually seriously?
Yeah. Yeah. I mean, that is really challenging because it isn't, a single metric. As you said, qubit count is not necessarily a great measure of the value of the uniqueness and the capabilities of that machine. We've had machines in the past with thousands of qubits. Actually, when I was at IBM, the roadmap, the technical roadmap, uh, resulted in a chip they called Condor, which was, I think it was 1,020 or 1,000. It was just over 1,000 qubits, and it had value in terms of the R&D effort that it took to design and fabricate that chip. But the connectivity of the qubits in that on that chip was so low, and the noise was really really difficult to maintain. So it really didn't see a whole lot of use, because even the researchers were like, there's a limited set of things we can learn from this, and then we'd like to go back to these 130 qubit machines that are actually much more capable. So the raw, qubit number was not an indicator of necessarily of progress towards utility milestones, right? Usefulness milestones. So what I like to say is obviously fidelity matters, noise matters, right? So the higher the fidelity of the 1 qubit gates and the 2 qubit gates, the meaning a logical operation that involves 2 qubits at once. So this would be entanglement in particular. Those are really, really important. But a proxy for those values is the resilience of the error correction code. So when you look at error correction in quantum, you talk about a distance or a D value. This is roughly equivalent to the number of errors that can occur in the system before the information collapses, before it's no longer what it's meant to represent. You've lost your computation. So the higher the distance, the more resilient that system is. And as an example, I think the Willow experiment a year and a half ago was distance 7, if I remember. So that was roughly 100 qubits in a surface code presenting as one logical qubit with a distance 7. So that's kind of a full snapshot that kind of incorporates, you don't even need to know what the gate fidelities are that underpin that at the physical level, because what's important to you as an end user is how many logical qubits do I get, and how resilient is that error correction. So that's kind of the cheat sheet version of evaluating the claims.
Mm,
However, that's complicated by the fact that we're still at a stage where there's anytime you hear somebody saying quantum computing is just a matter of engineering now, we've
mhm.
got the ingredients we need. It's just engineering. Be suspicious of that person's claims, because there's still fundamental science involved in a number of challenges across all of the modalities that all of the vendors are pursuing. It really is like the early days of classical computing, when it wasn't just, how do we fit more transistors on a chip? It was, what materials are appropriate for this? How do we, what's the right engineer, or what the fabrication process? There were really deep unknowns that we tackled as an industry that were very unpredictable in how long it was going to take. It was only, in aggregate, that you could say, oh, Moore's law doubled the number of transistors every 18 months. There was actually an incredibly broad set of really, really tough challenges that were being tackled all at once by a growing industry. And we're right at the very beginning of that in a lot of ways with quantum computing, where we don't have, because we're hampered by the fact that, an individual transistor had value, as an amplifier, as a filter, as all kinds of electronic kind of tasks that it could carry out, even in isolation in the 50s and 60s. You put a couple transistors together, you got a radio, right? I mean, you could make useful devices. We haven't gotten to that point yet. We might. Quantum sensing, actually, we haven't touched on it, but it's a very interesting sort of branch of the quantum technology family that might actually deliver value without universal computation. If we get to that point, I think that'll make things easier, because the challenge right now is that a qubit is a very interesting device with no intrinsic commercial value. And the challenge is to making it a commercially valuable device still involve fundamental science. So as an example, with superconducting qubits, for example, you've got them and a lot of other qubits as well. You've got them in a dilution refrigerator, right? You've got to keep them super chilled down to almost absolute zero. And a fridge has a limited amount of space. So in order to scale to a larger computer, you're going to have to connect the qubits in the bottom of one fridge to the qubits in the bottom of another fridge. That's commonly referred to as transduction, because you're going to need to transduce the frequency or the wavelength of the qubits in the bottom of the fridge to a photonic frequency, commonly used in telecom, so that you can convert the qubits in the fridge into what they call flying qubits on a fiber optic cable, bring the quantum value over to a qubit in another fridge, and then translate again into the native frequency or wavelength of the qubits in that superconducting device. That's there. All the ways we know how to do that transduction are not delivering the fidelity that's required for that device to actually operate reliably. So basically, we don't know what it's going to take to improve transduction. So that's sort of it's a scientific challenge, and it's one of many, many, many scientific challenges. And the thing with scientific challenges, it's not just hard work. It's a lot of hard work, but it's also luck, right? Because scientific challenges, we don't know what we don't know. You have to follow your intuition, follow existing science, and try things, and try to, basically create a hypothesis and then disprove the hypothesis until you find one that you can't disprove. And there's your working theory. And then the engineers can take over. So there's really, it makes it very difficult to return to the original question, to evaluate the claims of a hardware company, because it's speeds and feeds, right? It's the specifications on the paper. It's the roadmap that's projecting into the future. In 1 year we'll deliver this, in 3 years we'll deliver this, in 5 years we'll deliver this. That's an engineering document, and engineering is much more deterministic than the underlying scientific breakthroughs that are required to enable the engineering to deliver those milestones. So it's, when I talk to investors in the space, I encourage them to have very deep investigations in their due diligence when they're considering investing in a hardware company, and getting very comfortable with sort of the scope and the approach to the scientific challenges that still exist. So for the general public, it's sort of like very difficult to get to an assessment. I mean, but as I said, if again, to circle back once more to the classical computing industry, it almost doesn't matter for end users what the specific claims and challenges are of one vendor, because in aggregate, what's true is the industry is progressing, and we're progressing towards an agreed on, the consensus is we need to deliver fault tolerant logical qubits at a scale that is not simulatable by a classical computer. So that's the North Star we're all sailing towards. And for an end user, that's the only thing that's going to matter. Is once I can't simulate it on my laptop or my GPU cluster, then I'm going to have to do it on a quantum computer.
So thank you so much for elaborating on that. I do have a few more questions. I think what I'll do is, considering the time we have left, I will send them over an email to you. But maybe
Sure.
you could, just before we wrap it up, you could probably tell us what quantum ready actually means, or you could also tell us a bit more about, the people working in the domain, right? So what can they be expecting in coming years?
Yeah, quantum ready it's I mean, it has different meanings based on the context, but in general, I touched on it before. I think it means having some understanding or developed intuition around what a quantum information approach to solving a problem would look like, and whether that's reading research papers that describe a particular algorithm or aspect of quantum information theory, or for classical developers, for existing software developers, often the best way is to learn is through coding. And thankfully, the coding tools are very familiar, right? Most of the programming that goes on in quantum computing is done with Python. Qiskit I mentioned before is the IBM SDK. That's a Python SDK. Amazon's Bracket, I worked at AWS for a number of years. The Bracket SDK is also Python. There's a number of others that are Python or the other very well understood languages. The reality is that the way that you construct a task and send the task to a quantum computer it uses the tools that we're really familiar with. How the task is actually constructed, the logic of the circuit is where the difficult part is. So that means for a developer, there's all kinds of really easy entry points that can provide at least the beginning of making yourself familiar with quantum computing. And one of my favorite for a developer, one of the favorite ways that I recommend is I mentioned Unitary Foundation, which I'm a fellow at. We have an event every year called Unitary Hack. That's a remote. It's actually starting to become an in-person thing as well, but it's a global couple of weeks event where the maintainers of open source repositories of quantum software who participate can tag issues in their repo, and then developers can close out those issues and claim bounties for the issues that get closed out. The issues are often, housekeeping, administrative tasks, security tasks, things that are very familiar to classical developers and have to do with the capability and the resiliency, the maintainability of the package. But as a side effect, you get to see the insides of how that quantum software package works. My favorite example of how this can turn out is an engineer by the name of Misty Wall. She worked at ASML and mechanical engineer, I believe, or EE, and she was finished shipping a major project at ASML, looking for something to get involved in, and was interested in quantum computing. Didn't really have any particular background in quantum information. Got involved in Unitary Hack. Started closing tickets in error mitigation framework called MITIC. Error mitigation being almost like a building block towards error correction. It's you don't have full error correction, but you're trying to find ways to tease better signal out of the noise or separate the signal from the noise. So MITIC is an open source framework that you can experiment with different approaches to error mitigation. So she started in the Unitary Hack by closing out tickets in the MITIC framework. And then 2 or 3 years later, was lead author on research papers on quantum error mitigation. So she turned into, her experience brought her to being actually a quantum information researcher. Doesn't happen for everybody, but it's certainly a viable path. And I think, Unitary Foundation itself has a Discord year round. If Unitary Hack just happened in June, so if you don't want to wait till next June, there's a Discord server for Unitary Foundation, and all of the popular packages, the packages that have a lot of users, have a channel on that Discord, so you can sort of see what packages are out there. There's open source simulation packages, for example. Those are really good ways to develop a better understanding of how quantum circuits are represented, what those algorithms look like, because you're building a simulator to classically run a quantum circuit, and other types of packages. All kinds of really exciting work going on in the open source community. And for a developer, for end user, that's the best way in, because otherwise you need to go get a PhD in physics and get a job in a physics lab or at IBM or AWS or Google or somewhere, and get your hands dirty. And that's a very long path and not for everyone. It's extremely challenging kind of field to get into as a practitioner. But the good news is that their hard work has made it easier for us to just access real quantum computers over the internet using tools that we're all familiar with.
Interesting. Thank you so much, Sebastian. I think I posted a link to Discord. I just found it on Google and just
Great.
posted that in the chat. We'll also mention it in the newsletter issue that we make. I think this is how it's going to go. We are going to divide, a lot of that we discussed today into a newsletter issue as well as some articles, and I'll also follow up with you on the questions that we could not ask today.
Great.
But thank you so much for patiently answering, explaining. Really appreciate this is kind of the conversation we look for, and I'm sure people in the audience found it edifying. So thank you so much for joining us today.
Absolutely my pleasure, Saqib. Thank you for your questions.
Awesome. Well, if anybody has not signed up for a Deep Engineering newsletter, please sign up for that. And within a couple of weeks, we'll be sending out the newsletter issue. With that, thank you all for joining us today. Goodbye.
Thank you.